Good morning. It is a great pleasure for me to be here in Krakow attending IWOTA 2022. I'd like to give a special thanks to the organizers for the invitation to give this semi-plenary lecture. What I'd like to do is describe some joint work with Chafiq Benhida from Université de Lille and George Exner from Bucknell University on the connections between k-hyponormality and n-contractivity. Some of the key words I'm going to use in this talk: subnormal, weighted shift, Berger measure, Allouthke transform and Schur products, moment problems, Agler shifts, n-contractive shifts, completely monotone functions, completely alternating functions, moment infinitely divisible weighted shifts, also called MID shifts, Laplace transform methods, and conditionally positive definite matrices. We're going to start with Hilbert space, the algebra of boundary operators on H, and the notion of normal, T star T equal T star, subnormal, the restriction of a normal operator to an invariant subspace, hyponormal when T star T is bigger or equal to T star, and if we define bracket S comma T, the commutator of S and T, we can now talk about an n-tuple, T1, Tn, in jointly hyponormal when the self-commutator of the n-tuple, as defined here, is a positive operator function, operator matrix. And we say that an operator T is k-hyponormal when the k-tuple T squared T to the k is jointly hyponormal. And that means this self-commutator here being positive. It is well known that normal implies subnormal, implies k-hyponormal, 2-hyponormal, hyponormal, and subnormal also implies polynomially hyponormal, which implies weakly k-hyponormal and quadratically hyponormal. The celebrated Bram-Halmos result from 1955 says that an operator is subnormal if and only if it is k-hyponormal for all k. Namely, the k-tuples t squared t to the k are jointly hyponormal for all k. With Mihai Putinar, in 1991, we proved that polynomial hyponormality does not imply subnormality. That was an open problem from the formulated by Halmos. And then actually polynomial hyponormality doesn't even imply 2-hyponormality. So having polynomial hyponormality here doesn't even get you there to 2-hyponormality. N-contractivity, on the other hand, is defined using the so-called Agler sums. So sum from j equal 0 to n of minus 1 to the j, n choose j, t star to the j, t to the j bigger or equal to 0. And the Agler-Embry characterization states that for contractions, T is subnormal if and only if is n-contractive for all n. T is n-expansive if the above inequality reverses, and completely hyperexpansive if the reverse inequality holds for every n bigger or equal to 1. So in certain sense, CHE is an analog of subnormality, but when the inequality signs get switched from greater than or equal to less than or equal. Agler-Embry, together with Bram-Halmos, states that if T is a contraction, then T is k-hyponormal for every k, if and only if T is n-contractive for every n. So now we would like to see if it's possible to establish some kind of bridge between k-hyponormality and n-contractivity. Right now, what this theorem guarantees is that if I know that something is k-hyponormal for every k, then it is n-contractive for every n, and vice versa. So let's talk about unilateral weighted shifts. Given a bounded sequence of positive numbers, we form the operator on little L2 of z plus as W alpha ek equal alpha k plus 1 for all k bigger or equal to 0, where ek is the canonical orthonormal basis of Ln. Okay? So the moments of alpha are given as follows. You multiply the squares of consecutive weights beginning at 0 and ending at k minus 1. So you have a product of k factors here, and that's your kth moment for the sequence. standard notation for us will be, we will use Greek letters alpha, beta, omega for the weight sequence and gamma, gamma ray for the moment sequence. So gamma is reserved for moments, the other letters are reserved for the weights. The unilateral shift is the weighted shift with constant sequence 111. The Berger-Gellan-Wallen result says that weighted shift is subnormal if and only if there exists a positive Borel measure of mu on the closed interval going from 0 to the square of the normal W alpha that represents the moments of the sequence. So we can say that the moments of the sequence are the power moments of the measure, and mu is called the Berger measure of W alpha. The Berger measure of the unilateral shift is delta 1. The Berger measure of the Berman shift is Lebesgue measure on the interval 0, 1, and the weights are given like this. Okay, so k-hyponormality was characterized in 1990 as saying that the Hankel moment matrices starting at gamma L and ending at gamma L plus 2k has to be all non-negative as scalar matrices. All of these, an infinite collection of scalar matrices have to be non-negative Hankel matrices, and that gives you k-hyponormality. K controls the size of the matrix. So if k is equal to 2, we're talking about 3 by 3 matrices. Exner in 2006 proved that contractivity for weighted shifts is described in the following way. So this is analog to the Agler sum, but where instead of t star to the k, t to the k, we have now the moments gamma L plus j. And this has to be true for every L, and if n is fixed, that has to be true for every L. So it's kind of a infinitely many conditions again, where the n is fixed. Okay? So k-hyponormality is described by matrices, n-contractivity is described by Agler sums. When n is equal to 4, the expression can be regarded as an inner product of two vectors, at least in two different ways. I can think of this way, right? So gamma L, L plus 1, L plus 2, L plus 3, L plus 4, and then 1, negative 4, 6, negative 4, 1. That's one way to express it. But there is another way, which is as an inner product between two quantities, 1, negative 2, 1, and 1, negative 2, 1, acted upon by the 3 by 3 matrix gamma L plus 1, L plus 2, L plus 3, L plus 4. And you see what's happening here. This is one of the matrices we need to check two hyponormality of the weighted shift. So somehow it's telling me that if I knew that the weighted shift is too hyponormal, I will be able to claim that this inner product is positive, and that will be the Agler sum that we have at the top. So therefore, that will be the contractivity we want. So this latter option is actually optimal. So here is a key observation. If you take T gamma L2K to represent this BK transpose, where BK is the signed binomial vector. So it's not just the binomial vector, but with alternating signs, negative, plus, and so forth. And then notice that the sum of the entries of the BK is equal to 0. So 2K contractivity is detected by the positivity of the moment matrix on a suitable hyperspace of CK plus 1, the hyperspace where the vectors add up, the entries of the vectors add up to 0. And that has the ring of conditional positivity. Okay? But this in particular establishes that k-hyponormality implies 2K contractivity. Let's talk about Lutzke transforms now. So look at the polar decomposition of an operator, B times P, where B is a partial isometry and P is the positive part. In the Lutzke transform, we move half of the power of P to the left, so that now we have radical PV, radical P, and the iterates are formed in the same way. We have to recompute the positive part and move half of that to the left and so forth. But here are some facts about the Lutzke transform. The fixed points of the Lutzke transform are the quasi-normal operators. These are the operators in which the two factors in the polar decomposition commute, or also T and T star T commute. That's another way to define quasi-normality. Junko and Piercy proved that in 2000 that if the Allouske transform has non-trivial invariant subspaces, so does the original operator T. The Allouske transform is contractive. It follows that the iterations of the Allouske transform form a decreasing sequence of numbers, and Yamasaki exploited this to prove that the norms of the iterates of the Allouske transform decrease to the spectral radius of T, which is less than or equal to the norm. So one way to calculate the spectral radius, other than using Gelfand's formula, is to take iterates of the Allouske transform, take the norm from that, and then calculate the limit. Now, the Allouske transform of a weighted shift is again a weighted shift. Concretely, if you look at the weights of the Allouske transform, they are formed by taking alpha 0, alpha 1, alpha 1, alpha 2, alpha 2, alpha 3, and then square roots. And the reason for the different alphas is given because one of the square root p's act on the basis vector, and then comes the operator that comes the partial isometry, which is u plus, shifting the vector 1 and then one space, and then the radical p comes on the other side, and that's what creates the discrepancy between the two alphas here. One is alpha 1, the other is alpha 2, one is alpha 3, the other is alpha 4, and so on. Now, that brings into the surface the square root shift, which is a shift where you take the square root of all the weights, and we conclude that the Allouske transform is the Schur product of this shift and its restriction to the subspace E1, E2, E3, because one of them will start radical alpha 0, radical alpha 1, radical alpha 2, the other radical alpha 1, radical alpha 2, radical alpha 3, and then you multiply the two doing the Schur product, entry by entry, and so you get the Allouske transform. A sufficient condition for the subnormality of the Allouske transform is subnormality of the weighted of the square root shift. I should say right off the start that the subnormality of W alpha and the subnormality of the Allouske transform of W alpha are not equivalent, right? So here we have a sufficient condition for the subnormality of the Allouske transform in the subnormality of this, but this is not equivalent to the subnormality of W alpha either. Now, Exner showed that subnormality is not preserved on the Allouske transform. Concretely, he found an example. Here is the example. We had previously written a year earlier an example with Yun Tung Pung from Iowa State and Jasang Jung from University of Texas, Rio Grande, that this particular shift that has a 3-atomic Berger measure given as a convex combination of the delta 0, delta 1/2, and delta 1 is going to have an Allouske transform that is not subnormal. Okay, so let's talk about a little bit about Schur products. We're going to denote by circle red the Schur product, meaning that we multiply the sequences entry by entry, or we multiply the matrices entry by entry. So with Sansu Park, we show that if W alpha and W beta is subnormal, respectively k-hyponormal, then the Schur product is also subnormal, respectively k-hyponormal. Okay? What happens is that since subnormality and k-hyponormality are described in terms of Hankel matrices, positivity of Hankel matrices, and two positive matrices lead to a Schur product which is also positive, that's why the first result holds. And we also show that k-hyponormality of the powers, these are the regular powers of the operator W alpha, not the Schur powers, regular powers, is determined by the k-hyponormality of L shifts, 1, 2, 3 L shifts, that carry as weight packets of length L, starting in alpha 0, alpha 1, alpha L minus 1, and so forth. Okay, so this is how you detect the k-hyponormality and the subnormality of the powers of a weighted shift. Okay. Now, given W alpha and t bigger than 0, consider the weighted shift that is consisting of taking the tth power of the weights, right? For any t bigger than 0. So we're going to define W alpha to be moment infinitely divisible if the shift with weight sequence alpha to the t is subnormal for every t bigger than 0. This has immediate connections with with infinitely divisible matrices, right? In the theory of probability especially. And the connection is going to be that once I have the weights in this form, I can form the moment matrices associated, and those moment matrices then we have properties connected with infinitely divisible matrices. If W alpha is subnormal with Berger measure mu, under what conditions is W alpha to the t subnormal? If it is, how is the Berger measure of W alpha to the t related to mu? And when is a weighted shift MID? How can I characterize those weighted shifts so that every tth power is still subnormal? So before we deal with that, I want to show you a couple of staircases from hyponormal to subnormal. This is 2 hyponormal, 3 hyponormal, 4 hyponormal, and so forth. This is the Brown-Kalmosh staircase. On the other hand, there is Agler-Embry saying, well, 2 contracted, 3 contracted, 4 contracted, and so forth will also get you from hyponormal to subnormal for contractions, right? So at the very top, there is the MID level, which is a stronger condition than subnormality. And this is the condition that says every tth power of the operator of the shift is going to be still a subnormal weighted shift. So the result that I mentioned before, that the one that involved the special binomial coefficients, the sign binomial coefficients, tells you that 1 hyponormality implies 2 contractivity, 2 hyponormalities imply 4 contractivity, 3 hyponormalities 6 contractivity, and so forth. So those are 3 bridges that we have there, and of course there are infinitely many more, from 4 hyponormality, 8 contractivity, and so on. And we want to study in particular what happens to the Agler shifts and what kind of shifts we have here. You are familiar with the Berman shift, which is the one when j is equal to 2, but there are of course many others involving any number, any integer bigger than 2. So the Agler 3 shift, 4 shift, and so forth. They are all subnormal. And here is the Berger measure, which is not difficult to calculate. And A2 is the Berman shift. The remaining Agler shifts are the upper row shifts of the Drury-Arveson 2 variable weighted shift. So I'm sure you are familiar with Drury-Arveson shift. And then if you look at, I'm going to show you the diagram here. If you look at this weight diagram for the Agler shift, at the bottom you see the unilateral shift. Here's the Berman shift. Here's the Agler 3, Agler 4, and so forth. And here are all the Berger measures for that. Okay. So powers and Alloutsky transforms of the Agler shifts are again subnormal via an approach based on completely monotone functions. A completely monotone function is one where its derivatives alternate in sign. So here is the ones, the odd derivative, the even derivatives are non-negative, the odd derivatives are non-positive. F is completely monotone if and only if f is the Laplace transform of some positive measure. It's fact that if a completely monotone function f interpolates the moments of a shift, namely f of n is gamma n, the moment, then for all n, then the shift is subnormal. So this is one sufficient condition that you can use to check that your weighted shift is subnormal. You look at the gammas, and they happen to be the restriction of the function f to the non-negative integers, and the function f is completely monotone. Exner proved that if you look at the Agler shift, any pth power transformation is again subnormal, as is any mth iterated Rayleigh transform of HA. So all the Agler shifts, all the iterated Rayleigh transforms of the Agler shift, any power p, they are all subnormal. The proof, we use this monotone function theorem, really unfortunately offers no information about the Berger measure of the resulting shift. So using the difference operator, we can now rephrase the Agler-Emry conditions for the shift as follows. So this is nabla to the power 0 is the identity, nabla phi is phi n minus phi m plus 1. So it's the successive differences moving forward like this. And then you iterate the nabla to obtain nabla to the k. For example, if you look at nabla square, it's going to be phi n minus 2 phi n plus 1 plus phi n plus 2, and nabla cube will be this expression here, where you see the binomial coefficients coming up with signs, with the negative signs in the right places. So these are those special binomial coefficients that we discussed at the beginning. The sequence is said to be completely monotone if nabla to the k of phi n is bigger or equal to 0 for all k and n. And the Agler-Emry characterization of subnormality says that if T is a contraction, then T is subnormal if and only if T is n-contractive for all n. And it follows from the Agler-Emry conditions that the moment sequence is completely monotone in the definition that we gave before. So now, subnormality, that the moment sequence is completely monotone, or that the nablas are all non-negative, are equivalent. Now, a sequence is said to be completely alternating, where the inequality sign flips from being bigger than or equal to 0 to being smaller than or equal to 0, but it has to be for k bigger or equal to 1, okay? And equivalently, the sequence minus nabla is completely monotone. Similarly, given an integer k, the sequence is said to be k alternating if we have this true for all n bigger or equal to 0. Berg, Christensen, and Riesel proved in 1984 that psi is completely alternating if and only if the exponential of minus t psi is completely monotone for all t bigger than 0. So there was a concrete connection between completely alternating and completely monotone via the exponential map. Now, they also prove that psi is completely alternating if and only if it has an associated Levi-Khinchin measure, which is described here. This is similar to the situation we have with the Berger measures, but with an affine factor, affine term at the beginning. In the case of the Agler shifts, the sequence of weight square is here. And so you can now see that phi is completely monotone if and only if it has an associated positive radon measure on 0, 1, which is given in this manner. Right? So the phi of n has to have a measure here, which in the case of weight shift, this will be the Berger measure. And there is a nice connection then with the Levi-Khinchin measure associated with completely alternating functions and sequences. So here are two well-known key results. If psi is bigger than or equal to 0 and completely alternating, then the log of 1 plus psi is completely alternating. Tavale and Ranjikar and Berg, Christensen, and Riesel prove that if psi is bigger than or equal to 0 and completely alternating, then psi to the p is completely alternating for all p between 0 and 1. With Chafiq and George, we prove that psi is bigger than or equal to 0 and completely alternating, then log of psi is completely alternating. And as a result, we can find an psi bigger than or equal to 0 so that log of psi is completely alternating, but psi is not completely alternating. Okay? So it is possible for the log to be completely alternating, but the sequence psi not completely alternating. It's a complete example right there. Is built out of the Berman shift. There is a power 3, right? Okay, so here is the link between moments and weights. The moments are given by gamma n plus 1, and since they are given recursively, every time you multiply the square of another weight, we can write it in this form. This is it's akin to the formula for the factorial of a number, right? And so the log of gamma n plus 1 minus the log of n is the log of alpha n squared. Or if you want to write it in terms of the nablas and use mathematical induction, then you can prove that minus nabla to the k plus 1 of log of gamma is equal to nabla to the k of log of alpha squared. So we have a connection between the log of the moments and the log of the weights. So if log of gamma is completely monotone, then log of alpha squared is completely alternating. Let's discuss MID shifts a little bit. W alpha is MID when all the powers are subnormal. With Chafiq and George, we prove that W alpha is MID if and only if the alpha n's are less than or equal to 1. Alpha n squared is log completely alternating. And as a corollary, all angular shifts are MID, and also the contractive S, A, B, C, D shifts and their subshifts are MID. And here we have AM plus B over CM plus D with this proviso that AD bigger than BC. These are associated with fractional linear transformations restricted to the natural numbers. Okay. So if W is MID, then any power of W is MID for all power Q bigger than 0. And if W is MID and M is in natural number, then the subshift associated with this sequence is also MID. The quotient map says that if W is contractive hyponormal and if beta is alpha n over alpha n plus 1, then W alpha is MID if and only if W beta is MID. The limit in the uniform topology of the sequence of contractive MIDs is also MID. And if W is subnormal with Berger measure mu, and if there exists a sequence of Berger measures associated with MID shifts that converge to mu in the weak star topology, then the limit is also MID. So all of those are good things about MID shifts. In particular, the quotient map has a lot of applications. We can also improve on a result of Cohen and Long, who established the subnormality of a certain weighted shift of importance in considering Toeplitz operators. This is the solution, their solution of the Harmos problem 5 on the existence of a non-normal, non-analytic subnormal Toeplitz operator. And concretely, what we have is that the weighted shift that they consider was not only subnormal, but actually moment infinitely divisible, much better than that. And if you actually multiply several of these, you still get MID. Weighted shifts are determined by the Weyl sequences. This suggests that a sequential approach to study their positivity properties, and k-hyponormality and subnormality are characterized by the positivity of certain matrices, n-contractivity and complete hyperexpansivity detected by sequences. So we have a mix of sequences and matrices, both in the definitions of k-hyponormality, subnormality, n-contractivity, and complete hyperexpansivity. So here are some fundamental questions. Can all of these notions be described matricially? If so, can these notions be extended to boundary operators from weighted shifts? Is the class of weighted shifts essential for the descriptions or simply a test environment? Here is a revealing diagram. Weight squares completely alternating imply weight squares log completely alternating, which is a condition equivalent to MID. MID is equivalent to having the moments log completely monotone, where we have here, and then this implies that the moments are completely monotone. So you go from completely alternating for the weight square to log completely alternating for the weight squares, which is MID, across to MID in the moment version, which is log completely monotone, and that implies the moments completely monotone, which is simply subnormal, right? So we know that these two implications are strict, but we don't really know, we don't really have a good characterization of what it means for the weight squares to be completely alternating. It's certainly MID, but MID, what additional property? This is what we're missing, the additional property. What about Berger measures related to Agler shifts? As we know, if we take the Berman shift, the Berger measure is dt, and so what is the Berger measure of nu square? If I take the Berger the Berman shift and I take the Schur product with itself, I'm going to get another subnormal weighted shift whose Berger measure is given by minus log t. And in particular, dt squared is singular at the origin, right? We started with the continuous measures, and by taking the Schur product and calculating the Berger measure, now we have a singularity at the origin. As a corollary, the Lutzke transform of the weighted shift associated with the Berger measure minus log t dt is A3, the third Agler shift. So start with the Berman shift, take the Schur product twice, and then take the Lutzke transform, and then you end up with the Agler shift. But this only holds for that particular Agler shift. We thought that it would be more general, but that's the extent of what is true. Atavale in 2013 showed that the Berger measure for radical dt, so now this time taking the square root of the Berman shift, is represented in this manner. And our proof of a more general result uses Laplace transform methods. And our more general result is that if we look at the qth power of dt, we can express it as in this manner with the gamma function. We still got the minus log t, just as in the case of Atavale, but in a more general situation. So f dt is the Berger measure of the weighted shift with moment sequence given by 1 over n plus 1 to the q between n equal 1 and infinity. And again, as a special case, you get the square root of dt, which is what Atavale had gotten before. Okay, here's a theorem. Suppose that W alpha is a contracted hypernormal weighted shift. Hypernormal means that the weights are non-decreasing. The following statements are equivalent. W alpha is MID, W square root alpha, the Schur square root is MID, the Lutzke transform is MID. So while it is not true that W alpha subnormal and W radical alpha subnormal are equivalent, at the level of MID, they are. Okay? So all of these properties are equivalent if I'm dealing with a class of moment infinitely divisible weighted shifts. A Lutzke transform, square root shift, and the original weighted shift. So we know that in general the Schur square root is subnormal. The original shift is if the square root is subnormal, then the Lutzke transform is subnormal, but the reverse question remains still open. The Lutzke transform maps MID bijectively onto MID. So here is the result from the paper in 2020, where the Lutzke transform is MID if and only if W is MID. If W alpha and W beta are MID, then the Lutzke transforms are the same, then the shifts are the same. And if W beta is MID, then there exists the W alpha MID such that AT of W alpha is W beta. So there is a nice mapping between MID shifts provided by the Lutzke transform. One of the things that we have tried to do is to study the consequences having that bijection at the level of the MID class. So each Agler shift is the Lutzke transform of some MID shifts, which we are able to compute. Okay. Now we're going to switch to positive definite matrices, and as is common in the literature, the expression PD stands for positive semi-definite. So we will simply say that a matrix is positive definite in symbols a bigger or equal to 0 if A is Hermitian and B star AB bigger or equal to 0 for all vectors. Right? So here are some canonical examples: the Grand matrices, the Hilbert matrix, the Pascal matrix, the Lemmer matrix, the GCD matrix. These are all matrices which are infinitely divisible. Namely, you take any power of them, positive power, and you will continue to keep the positivity. It is easy to see that all positive definite 2x2 matrices are infinitely divisible. It's just an exercise. But here comes a 3x3 matrix for which this is not true. So this one here is positive definite for all A between 0 and 1, but the determinant of RA to the 1/2, if I were to take the square root of this positive matrix, calculate the determinant is negative for small positive values of A. So near the origin, you have non-positive definite square roots. A Hermitian matrix is conditionally positive definite, CPD, whenever you look at C star AC, and it gives you a non-negative number for all complex vectors that satisfy, in addition, the condition C0 plus C1 plus CK equals 0. So you are restricting attention to vectors in the hyperspace given by hyperspace of codimension 1, given by this expression here. An infinite matrix is CPD if and only if, an infinite matrix is CPD if all its principal minors of finite size are CPD. Now, clearly PD implies CPD, because we check all of the vectors, not just those vectors. When k is equal to 2, A is CPD if and only if A11 minus A12 minus A21 plus A22 is equal to 0. So it's like a complete a determinant that is badly computed using sums instead of products. A11 plus A22 minus A12 minus A21. When k is equal to 3, A is CPD if and only if this 2x2 matrix is PD. And this is a general result. To check CPD, you can take a transformation into a matrix of one size lower and check whether that is positive definite. So here is CPD has at most one negative eigenvalue. If A is non-zero, has non-positive entries, and is CPD, then A has exactly one negative eigenvalue. Consider a contracted unilateral shift, MID, and its moment matrices M gamma 0 and M gamma 1. So these are the Hankel moment matrices starting at gamma 0 and starting at gamma 1. Then log of these matrices are non-zero matrices, have non-positive entries, are all CPD. So each of these matrices has exactly one negative eigenvalue. Here is a theorem. If you take a Hermitian k by k matrix, the following are equivalent. A is CPD. Phi of A, this transformation that adds the two diagonal elements and subtract the two off-diagonal elements for 2x2 minors is PD. And there exist real numbers omega I such that Aij minus omega I minus omega j is PD. And for all p bigger than 0, the matrix e to the PA is PD. All of these are equivalent conditions. And so here is the transformation that we saw before that takes you from CPD to positive definite. CPD matrices are intrinsically associated with distant matrices and also with the ground matrices. So given A CPD, one can find D bigger or equal to 1 and K points in RD, so that A minus 2G, the ground matrix associated with that, is in the kernel of phi, where G is the Gramian induced by the P's. So distance matrices are a good thing to keep in mind in terms of thinking about CPD matrices. The remark, if A is k by k with positive entries and assume that minus A is CPD, then the k by k matrix of reciprocals is infinitely divisible. And Lerner showed that if M is symmetric matrix positive entries, then M is infinitely divisible if and only if the log of M, meaning the Hadamard logarithm, taking the log entry by entry, is CPD. This is a very nice result, checking the infinite divisibility by computing the log and checking that it's CPD. So let's consider the following two matrices. In our case, these are now weighted shifts, and these are the moment matrices associated with these two. These are the matrices that Stieltjes in 1894 considered to solve the moment problem for the positive part of the real axis. And then look at the weighted shift. W is MID if and only for each I, and each k, the log of M gamma ik is CPD, or equivalently, both the log of n gamma 0 and the log of n gamma 1 is CPD. As a corollary, if W alpha is a weighted shift, then the power P is k-hyponormal if and only if this log matrices are CPD for each I, but keep in mind that we are restricting attention to size k by k. Right? So the following result produces a new class, I should say k plus 1 by k plus 1, when you take, and then you take the log. Yeah. The following result produces a new class of subnormal weighted shifts. The proof uses the fact that phi of these is equal to the sum of the logs, but then that's the log of this quotient here. So if you take a weighted shift with moment sequence gamma, the following are equivalent. MID, this sequence is still just moment sequence, and the weight sequence of moments is subnormal. Okay? So delta n over delta 0 is a sequence of moments that is subnormal. Oh, let's characterize now moment infinitesibility in terms of CPD. Contractive weighted shift, m gamma 0, n gamma 1. As above, the following statements are equivalent. W of alpha is MID. The logs are CPD for every I and every K. The log of MIK is CPD. For every P, the powers P, Schur powers, are positive definite. And for every P, the Schur powers are CPD. And the moment sequence gamma is log completely monotone. And the weight sequence is log completely alternating. Of course, we knew the characterization between one and the last two, but the others are new conditions, but involving CPD. In view of the result in this section, one can try and extend the notion of moment infinitesibility for weighted shift to arbitrary contractions using the polar decomposition. So we are going to pursue this in a forthcoming paper. But the idea is that you look at the polar decomposition and then you use the absolute value of t to insert the power p, just as what Professor Daoxin Xia did when defining semi-hyponormality for operators. Instead of taking the absolute value of t and absolute value of t star, he was taking half of that, right? We recall that absolute value of t has already been there. Okay. In closing, I like to mention two recent papers on CPD, one by Zenon Jablonski and with Ilwan Zhong and John Stochel, and the other with the addition of Yunmin Li. And then these two talk about conditional positive definites in operator theory and also for unilateral weighted shifts. The author studies CPD conditions for operators on Hilbert space. The focus is on CPD sequences of exponential growth, with emphasis given to criteria for positive definiteness. In the case of weighted shift, they characterize CPD in terms of formal moment sequences. There are some references. We have the four papers with Chafiq and George that I mentioned at the beginning, and I'd like to thank you for your attention. Thank you.